Continuing example 3 from the section 4.5 notes, we're attempting to determine the amount of carbon-14 that would be remaining in an artifact from the reign of King Tutankhamun of Egypt. And thus far we've been able, by using the half-life of carbon-14, to determine that the decay constant is approximately negative 0.00012. So at this point our model is A of t equals A0 e to the k, so now I'll use negative 0.00012 times t. Now to determine the amount of carbon-14 remaining, we need to know how much time has elapsed. We know that King Tut died in 1346 BC. The current time, we're going to use the value in the problem, is 2014 AD. So the amount of time that would have elapsed would have been 1346 plus 2014. That gives us 3360. So 3,360 years have elapsed since the death of King Tut. So we're going to use that for our value of time. And so basically what we need to determine is A of 3360. So we're going to compute A of 3360, the amount of carbon-14 remaining after 3,360 years. Now we don't know the initial amount of carbon-14, but actually we can answer the question posed in the problem without knowing a specific initial quantity. In fact, it would really not be possible to know what that quantity was. So A0 e to the negative 0.00012 times 3360. Okay, now we need to compute the product in the exponent there. So let me do that. So I write A0, excuse me, I must have hit something on my screen to cause that window to pop up. A0 e to the negative, the product of the two numbers in the exponent is negative 0.4032. 4032. Then, using a calculator, using the second ln function on our calculator, we can approximate e to the negative 0.4032. So this would be approximately A0 times 0.67. In other words, 67% of A0 remains. So the amount of carbon-14 remaining in an artifact from the reign of King Tut should be, at the present time, approximately 67%. Our next example, example 4, looks at population growth under what's called the logistic growth model. The logistic growth model assumes that there are factors that limit the growth of populations. These are environmental factors such as limits to resources and things of that nature. If 10 wolves are introduced into a wildlife refuge, and it's assumed that the maximum sustainable wolf population is 100, the population would grow according to the logistic model P of t equals 100 over 1 plus 9 e to the minus kt. Notice the graph is shown what's called a logistic curve or a sigmoid curve. It's kind of a elongated S shape, And you can see that the population begins to level off, and the rate of growth slows down as the population approaches what's called the carrying capacity, which is the maximum sustainable population. And you can see that occurs at 100, and that there's a horizontal asymptote at that population. So the curve is showing the wolf population as a function of time in years, and you can see it's leveling off as you approach the 10-year mark. Show that P of 0 equals 10. That is, the initial wolf population is 10 according to this model. If the wolf population doubles after 1 year, what is the predicted population after 5 years? So we're going to try to determine all of this algebraically. First of all, show that P of 0 equals 10. Okay, so we're going to use our model 100 over 1 plus 9 e to the minus kt. Let t be 0. So P of 0 would be 100 over 1 plus 9 e to the minus k. We don't know what k is at this point, times 0. As it turns out, for this step, it doesn't really matter what k is. We don't really need to know it. We're multiplying it by 0, so that whole exponent just becomes 0. So we would have 100 over 1 plus 9 e to the 0. But e to the 0 is 1. So we have 100 over 1 plus 9 times 1. That is 100 over 1 plus 9, which is 10. And 100 divided by 10 is 10. So the initial population is 10, and that's the point that we see at t equals 0. You can see that the curve starts at p equals 10, exactly as the model would indicate. Now, we're also told the wolf population doubles after 1 year. We can use this information to determine the growth constant k. So if the population doubles after 1 year, that would tell us that P of 1 is twice 10, that is 20. Now, substituting t equals 1 into our logistic growth model, we would have 100 over 1 plus 9 e to the minus k times 1. That is 100 over 1 plus 9 e to the minus k. So notice what this gives us is an exponential equation, because the unknown k is in the exponent, with k as the only unknown. Because the left-hand side is 20, the right-hand side is what I've just written there at the end, 100 over 1 plus 9 e to the minus k. So how do we solve for k in this case? Well, what we need to try to do is to isolate the factor e to the minus k. And the best way to do that in this case is to first eliminate the fraction. So what I'm going to do is multiply both sides of the equation by the denominator. 1 plus 9 e to the minus k. I'm going to multiply 20 by that, and then I'm going to multiply the right-hand side of the equation by that as well. So what I'll do on the right then is I'm able to cancel that denominator out. So what I'm left with, let me write the left-hand side with the 20 out in front. 20, 1 plus 9 e to the minus k equals, and on the right-hand side then I just have 100. So you see what I've been able to do is eliminate the fraction, and that's going to make solving for k much easier. The next step that would make sense would be to divide both sides by 20, particularly since 20 divides evenly into 100. So if we divide both sides by 20, we obtain 1 plus 9 e to the minus k equals 5. Then if we subtract 1 from both sides, and I'll have to move over to the other side of the screen here now. If I subtract 1 from both sides, I would have 9 e to the minus k equals 5 minus 1 is 4. Divide both sides by 9. And then to solve for k, take the natural log of both sides. So the natural log of e to the minus k would equal the natural log of 4/9. On the left-hand side, that's just going to give me minus k, since ln and e cancel. Then again, natural log of 4/9. And then if I multiply both sides by -1, I obtain k equals minus the natural log of 4/9. Now the natural log of 4/9 is a negative number, so when we put a negative in front of that, we obtain a positive number. I'm going to round this to 2 decimal places. It's approximately 0.81. So the growth constant for this particular situation is positive 0.81. So now at this stage, our population model would be given by 100 over 1 plus 9 e to the minus 0.81t. Now keep in mind the logistic model includes a negative sign in front of the value of k. So even though k itself is positive, there is a negative sign that has to be placed in front of it due to the construction of the model. So we do see a negative sign there. Now what we want to do is determine what's the predicted population after 5 years. That would be P of 5. And using the model I just wrote, 100 over 1 plus 9 e to the minus 0.81 times 5. All right, then just simplifying a little bit more, if we multiply the expressions in the exponent, we would obtain 0.81 times 5 is 4.05. So I'm going to write e to the minus 4.05. And finally, we can use a calculator to approximate this expression to determine the number of wolves after predicted after 5 years. When you use your calculator, as we've mentioned before, you need to put parentheses around the expression in the denominator, even though when you write it you don't have to do that. You'll have to enter this basically as it's shown on your calculator using your second ln function, and what you should obtain is approximately, to the nearest whole number, 86. So we would predict 86 wolves after 5 years according to this logistic growth model. We'll continue with example 5 in the next video.